let Pn be a mathematical statement such that P1 is true. Okay. Let Pn be a mathematical statement, and let's write here n is a natural number such that P1 is true. Then Pn, then such that P1 is true. Let me write this as such that number one, P1 is true, and secondly, Pm plus 1 is true whenever Pm is assumed to be true. Where m is a natural number. This is the statement of mathematical induction. Okay, the application part is important. I've just stated this for the formal purpose. Let us look at the first question. Okay, just a demonstration of mathematical induction. Question number 1a. The question here is prove by induction. It's right here to prove. Now this is one result that you know, right? Square of first n natural numbers. We have discussed this under which chapter? Under which chapter have we discussed this result?
AP.
AP. N into n plus 1 into 2n plus 1 by 6. Right? Now, the independent proof of this result exists in AP. But we are going to prove the same result by mathematical induction. As I told you, mathematical induction is a very, very general tool. You can apply to any branch of mathematics. Okay. So you need to prove this statement. Okay. I start by saying, let Pn be the given mathematical statement. 1 square plus 2 square plus 3 square and so on. This statement, I don't know whether it is true or not. I have to prove whether this is true, but I am assuming this statement. Whether true or not, I will see later. Okay. Let Pn be this statement. Okay. Now for n is equal to 1. For n is equal to 1. What is the left hand side for n is equal to 1 of the given statement? Only 1 square, isn't it? We only take one term, which is equal to 1. What about the right hand side? 1/6 into 1, 1 plus 1, 2 into 1 plus 1, isn't it? Which will again give you 1, right? So for n is equal to 1, left hand side is equal to right hand side. That means this mathematical statement holds for n is equal to 1. So then what can you say? Thus P1 is true. Understood? That means this is satisfied,
Yes, sir.
right? Now we come to see, now we'll check whether this is satisfied or not. How will we check? First of all, if you read this statement, it says Pm plus 1 is true whenever Pm is assumed to be true. Okay, that means I assume Pm. Let's say let Pm 1 square plus 2 square plus 3 square plus up till m square is equal to 1/6 m into m plus 1 into 2m plus 1 be true. I have assumed this to be true. Okay. Now, assuming this to be true, I will show that Pm plus 1 is also true. Okay. Now, Pm, I have assumed this to be true. Then what is Pm plus 1? We have to show that Pm plus 1. And what is the statement? 1 square plus 2 square plus 3 square up till m square plus m plus 1 square is equal to 1/6 m plus 1. Replace m by m plus 1. M plus 1 plus 1. Okay. And twice m plus 1 plus 1 is true. This is what we have to show. That is, we have assumed this and we are going to show this is true. Okay. So how do we show? We start with the we start with the statement that we have assumed. So we have 1 square plus 2 square plus 3 square and so on up till m square is equal to 1/6 m into m plus 1 into 2m plus 1. Right? Now, if you see pm plus 1, this entire thing is there here. Right? What is missing only here? This one. So what we do is we add these m plus 1 whole square to both sides. So 1 square plus 2 square plus 3 square m square plus I add m plus 1 whole square to both sides because I need to prove pm plus 1. So I am trying to get to pm plus 1. Okay. 1/6 m into m plus 1 into 2m plus 1 plus m plus 1 whole square. What have I done here? Adding m plus 1 whole square to both sides. Right? So I've got the left hand side of pm plus 1, isn't it? This entire have I got here? Yes. What only remains to be shown? Only this part, right? So I work with this part. So which is equal to 1/6. Now if you see, I can take m plus 1 common here, right? So if I take m plus 1 common from the two, what am I left with? 1/6 m into 2m plus 1 plus m plus 1, right?
Yes, sir.
Which is equal to m plus 1. And now if I can take the LCM here, I'll get LCM as 6. So m into 2m plus 1 plus 6 into m plus 1, isn't it? Right? What are we trying to show? We are trying to show this. Right? Yeah, we'll express this as this because we have already got the left hand side part. Only the right hand side part we need to show. We get m plus 1 and you have 2m square plus m plus 6m plus 6 divided by 6. Right? So m plus 1. Let's take 6 out. And what am I left with here? 2m square plus 7m plus 6. Right? So we get m plus 1. Now 2m square plus 7m plus 6 can be factorized by your middle term factorization of trinomials. What will the two factors be? 3 and 4. So which is equal to m plus 1 by 6 into this. You can take m common from the first two. And here you can take 2 common. This is 2m plus 3. So you're getting m plus 1 by 6 into, and this can be written as 2m plus 3 into m plus 2. Okay. Now check. This can be written as 1/6 m plus 1, right? And m plus 2 can be written as m plus 1 plus 1. And what can 2m plus 3 be written as? Twice m plus 1 plus 1. Can I write this or not?
Yes, sir.
So have I got pm plus 1?
Yes, sir.
Yes. So assuming pm, we have proved pm plus 1. So this shows that pm plus 1 is true whenever pm is assumed to be true for m as a natural number, for m belongs to n. Hence, by the principle of mathematical induction, because both the conditions have been satisfied. The first condition was satisfied here when I showed Pm to be true, and here I have shown that in all these I have shown that Pm plus 1 is true whenever Pm is true. Hence, by principle of mathematical induction, both the conditions have been satisfied. Induction Pn 1 square plus 2 square up till n square is equal to n plus 1 into 2n plus 1 is true for every natural number n. Yeah, induction.